Thanks everyone for sitting through this with me. My name's Joe Tufts. I work at Semiconductor Technology Associates. We abbreviate that STA internally. I don't know why we came up with such a long name when we did. I wasn't there. You can reach me at the email address, either of the email addresses on there. The 3 people listed on the talk are the 3 primary people. We've got 5 in the whole organization. If you send an email to customer service, you reach us all. We read all of the emails. We respond to all of them eventually. We're coming up on what I would consider the 50th year anniversary of STA heritage. This started back when Dick Bredhauer did his thesis at UCSB just up the road on CCDs, and it's kind of snowballed from there. I'm going to not talk too much about this, but I'm going to say that I personally love astronomy stuff, astronomy CCDs, and we have a lot of our focus has been on astronomy CCDs through the years. We design and make the CCDs, controllers, and cameras that a lot of you guys in the room are using. I wanted to, because not everybody in the room is familiar with how CCDs are produced, I wanted to briefly go over that process, and I'm going to be skipping through. I bit off way more than I could chew with the talk, so I will try to get through this quickly. And I brought some stuff to show, and if I don't touch on it, please come see me in the coffee break and we can talk more if you want to. CCD starts with a design, and this is we do all of the design in-house for our CCDs. And over the years, I think it would be fair to say that we've got over 1,000 different CCD designs in our wafer room at work. And this is how it starts. And we draw that in, it's not really a CAD program, it's more of like a vector image editor, but it's got some features that make replication really nice. This is what the real guts of the CCD are. This is the guts of where everything happens on the CCD. In the upper left, you've got 4 pixels shown, and then those transfer down into a serial register, and then to the right towards an output node, which is I don't know if my pointer's going to work. No, sort of in the center of the figure in green with the 4 dots on either side of it. That's the output node, and that's the output amplifier. The yellow is an important region. We call that the buried channel, and that's very critical for getting your photons to the right spot. If that's not done right, you don't, sorry, not getting your photons, getting the electrons produced by the photons to the right spot. If that buried channel is not produced right, you don't have good charge transfer, you get lines that aren't symmetric, all kinds of sorts of problems. The blue is conductors. This is what we call a 3-poly process. There's 3 layers of polysilicon that are used as conductors that create the gate electrodes that move charge around on the CCD. From that design, we produce typically about 12 masks to make a single CCD. The fab that we use actually produces the mask, but we've learned that over time we have to talk directly with the mask manufacturers. This is a CCD mask. Come see this. It's really kind of cool optically if you do optics. This is one of the 10K masks that we use. We don't use that one anymore. That's why it's here. You guys feedback problems that we have, and we roll that into iterations. So we're still making, STA 1600 is the 10K that we make, and that's been made for 18 years now. But I think we're in Rev G of the mask set on that, and that's due to feedback from you guys. We draw these masks with 10 nanometer pixels. It's an electron beam drawing process, and that came primarily out of Express when they found that they were seeing in the first Express CCD, we were seeing periodic structure. We went back to the manufacturer and found that there's not just a high resolution and an ultra high resolution, but there's like a super ultra high resolution that we can write masks with. And so each pixel on our CCD is drawn with about 900 by 900 pixels on the mask, which is pretty cool. So this was sort of how the original 10K mask produced flat fields, which was not a big deal for photometry users, but it is a big deal for EPRV users because that's directly that's a periodic pattern directly on top of your spectrum. This is what it looks like when you produce masks with a better resolution. You can see on the bottom sort of residual PRNU stuff. And PRNU in EPRV means radial velocity errors. So we clean that up. After mask fabrication, we buy wafers we produce CCDs in 3 different thicknesses with 19 micron epi. Wow, I'm running way out of time. 30 micron epi and with bulk epi. And I wanted to put this up because it's just a big extreme number. I did the calculation on what the concentration of dopants is in our purest silicon. We say that, somebody was saying earlier today that if you breathe on the fibers, this is Eikenberry, that they'll change the modes. If you breathe on the 10 kilo ohm centimeter silicon, it changes its doping concentration. The stuff is so pure. We're talking like countable numbers of atoms inside of dopant atoms inside of pixels. Then we go to liquid lithography. We're making wafers at 2 different fabs right now, DALSA and Microchip. We make a 6-inch wafer at DALSA and an 8-inch 200 millimeter wafer at Microchip. This process, the lithography process, which I called fab until I got into this, under this side of things, is really about 250 steps, all with independent parameters, and that's sort of where the secret sauce and the magic happens. Takes about 3 to 6 months, and the most important things are the channel stop, or sorry, the channel, the buried channel, the stops on that channel, which define, in our case, the columns of pixels, and the mask alignment. Just going to skip through some of this. I do want to say that as we're going away from DALSA and to Microchip, we're going to have to start using stitching masks, which we've never done before. We've always made all of our CCDs in one big mask. But that is working. This is from the first device out of DALSA, or sorry, out of Microchip. There's a representation of the stitching errors. We can talk about that offline. Also, with stitching, we can make much bigger CCDs. This is our current, I believe this is the current world record holder for the largest CCD ever made. It's 120 millimeters square, 8K by 8K. Then after that, it goes to thinning. And this is a critical part. We do 2 types of thinning, die level thinning, which Mike Lesser in Arizona does, and wafer level thinning, which we do at a number of different places, and they have different advantages and disadvantages. And dicing and packaging, and now we're to the heart of the talk with 4 minutes to go. Great. I do all of the characterization for all of the CCDs that leave STA and go into your hands. So if you have questions about how that's done or want to add sets of data to your devices, then give me a call. I'm happy to talk about it and probably do it. This will be much more fun if you have more time. As I said, PRNU is flat field non-uniformities that directly translate to radial velocity errors. And I am interested in what I can do in the lab to measure PRNU or specifically offsets and stitching that might feed back into usable data for you guys in the field. And I'm curious if we can do this with a flat field or if I'm working on an interferometer to actually measure the offsets. But that's a long, slow process because there's not a lot of demand for it. I loved Molly Kate's talk about etalons. We build our own etalons as well in the lab unintentionally. This is the CCD thickness acting as an etalon. And what I'm doing in what you saw scanned through there was me moving the color of illumination in the flat field. And so I can change the fringing pattern and then measure it extremely well, and then measure the thickness of the CCD. Now that's fixed, and so in theory that could be used permanently in data. It doesn't change ever from the time of manufacture to the time of death of the CCD, which hopefully is very long into the future. And so that's one of the things that I would like to measure and use in a way that can help feed the data reduction process. So this is interesting that in doing this, I found on this particular device that there's actually 2 different interference fringes patterns imprinted on top of one another. One's due to actually the glue underneath the silicon, the other is due to the thickness of the silicon itself. Charge transfer efficiency, this was talked about yesterday by Xavier, I believe. And we characterize this in one of three ways in the lab. With iron 55 is the traditional way. It's not very fast, it's very difficult to do in the lab. EPER, extended pixel edge response, is the more common way. I kind of feel like this is a global phenomenon that's not, or a global measurement of a localized phenomenon that's not really what we need to be doing. So I'm looking at measuring traps on the individual pixels within the serial register and the individual pixels within the image array. And I do this by shuffling charge back and forth. And the idea is that the charge, when you move it one direction, will collect in a pixel more quickly than it releases from the pixel if there's a trap. And so you can see in this plot on the bottom that the lines are not always from the same direction. We're clocking towards the left, and sometimes charge is delayed. And then when we clock towards the right, sometimes charge is delayed in that direction. And so by using this technique, I can find the traps extremely well. I can find that it's very much, the traps are very much reduced if I slow down the clocking. This was probably obvious, but what was not obvious to me is how dramatic it slows down and where it reaches an asymptote fairly close to zero if you run slowly enough. It scales with the number of shifts I do, so we can extrapolate this. We've got a noise, or it's a noise floor where we have to do a certain number of shifts to even see the signal in the first place. And then it doesn't depend linearly on exposure time. And my theory for this is that as the pixels fill up with charge, they mask some of the traps. And so I think there's something to be done in this. And this is a very easy measurement for me to do in the lab and just add to the data set that comes with the CCDs. And I don't have more time to do this. So if you want to see the rest, then come see me.
That was perfectly timed. Thank you for ending on time. Okay, questions? Andreas, over here in the front.
Yeah.
He needs a microphone.
Again, I apologize for dwelling on the fabrication aspects a little bit too long.
Hey, Joe, great to see you. And
hey,
great to see you talk. One issue that you haven't really touched on is flatness. And I think that gets harder the larger the CCD area becomes. Is there something that can be done about this to improve the flatness?
While we're answering questions here, if you are giving a poster pop, please come up and line up in the order that Ellen sent you, and Ray will help you line up. Okay, do it quietly so we can hear the questions and answers.
Andreas asked about flatness on the sensors. We have an ability, which Andreas knows well, to measure that extremely precisely. I think that the flatness issues that we're seeing have very little to do with the packaging of the devices and more about the thinning of the devices. And so as we move to the microchip foundry and start playing a little bit more with wafer scale thinning instead of die thinning, I think that you'll see the flatness that we're currently seeing improve. The current numbers are on the 10K, we typically see below 50 microns, or a flatness better than 50 microns on the 10Ks. And I think you'll see that improve maybe by a factor of 2 with wafer level thinning. Xavier.
Okay, one more question up here, well, because we're still getting people in line.
What are your thoughts on like the...
You need a microphone, sorry. Because the people online can't hear you without the microphone.
Hi, about thermal conductivity and thermal anchoring to the CCDs for uniform cooling and anything like that?
Thermal conductivity within the CCD or within the packaging of the CCD, or do you just in general? General. So silicon conducts heat really well, and aluminum conducts heat pretty well. We've started packaging most of our devices on a silicon aluminum hybrid called CE6. It's got a thermal conductivity that's pretty close to aluminum and a thermal time constant that's very close to aluminum. It's significantly better than Inbar or any of these other materials. Silicon carbide's another contender. It's a lot more expensive for us. It's about 20 times more expensive to package a device on silicon carbide. I prefer to package the heaters and sensors into the CCD packages themselves, because I think that reduces the thermal time constant and will help improve the settling and the stability of the devices. I think is that fair to assume that's where you were going with the question?
Yeah, that's where I was going.
Okay.
Thank you.